Hello, everyone. I'm Dr. Orion, and I am thrilled to begin our journey into atmospheric science. We are starting today with A Tale of Three Planets, a fascinating look at how three worlds that started similarly ended up with such vastly different environments. Take a look at Venus. It's often called Earth's evil twin. Despite being roughly the same size as our home, its surface is a scorching 460 degrees Celsius. That's hot enough to melt lead. And the pressure? It's like being nearly a kilometer underwater on Earth. Our Earth, by contrast, sits in a delicate balance. With an average temperature of 15 degrees and a stable 1 bar of pressure, it's the perfect Goldilocks zone for life to thrive. Then we have Mars, the red planet. It's a freezing, thin-air desert. With an average temperature of minus 65 degrees, it has almost no atmosphere to trap the sun's heat, making it a very hostile place for liquid water. The most important lesson here is that distance from the sun isn't the only thing that matters. As we move through this course, we'll see that it's actually the atmosphere that dictates whether a planet is a frozen wasteland or a pressure cooker. Building on our look at the three planets, let's dive into why we call Mars the red planet. It's not just a clever nickname, it's a direct result of the planet's chemical makeup. The surface of Mars is covered in a layer of fine dust called regolith, which is heavily saturated with iron oxide. To put it simply, the Martian surface is literally rusting. Maya, you'll find this interesting. This formula represents the formation of hematite. Over billions of years, even with a thin atmosphere, enough oxygen interacted with the iron in the crust to create this global oxidation. Now, look at this bar chart. It compares the iron content in the crusts of Earth and Mars. You can see that Mars has a significantly higher proportion of iron available at the surface, which provides the raw material for its iconic color. As we see in this landscape image, that red hue is everywhere. Leo, imagine standing there. Everything from the rocks to the sky would have a dusty reddish tint due to the global dust storms mentioned here. These high-velocity winds pick up the fine iron oxide particles and spread them across the entire globe, ensuring the planet remains the rusty planet from pole to pole. Next, we'll examine the specific properties of the atmosphere that allowed this to happen. Building on our look at the surface rust, we need to examine the thin blanket of air that surrounds Mars today. It is a ghost of its former self. Let's start with the gas composition. If we look at this pie chart, we see that the atmosphere is almost entirely carbon dioxide. Specifically, it's about 95.3% CO2. Now on Earth, CO2 is a powerful greenhouse gas that traps heat, but on Mars, there's a major catch. The density is incredibly low. This bar chart illustrates the dramatic difference in surface pressure. While Earth has a thick atmosphere that supports liquid water, Mars is barely holding on. As NOVA would confirm from the data, the Martian pressure is only about 0.6% of Earth's. It's so thin that if you stood there without a pressure suit, your blood would literally begin to boil at body temperature. So, what happened to the rest of the air? The answer is atmospheric escape. Billions of years ago, Mars lost its global magnetic field. Without that shield, the solar wind, a stream of charged particles from the sun, slowly stripped the atmosphere away into space. Now that we've seen why Mars is so cold and thin, let's look at its polar opposite. Meet Venus, often called Earth's evil twin. While it is nearly the same size as our home, its surface conditions are a literal hellscape compared to the Martian deserts we just discussed. First, the heat is staggering. We are looking at an average surface temperature of 475 degrees Celsius. Leo, if you tried to land a probe there, it would have to withstand temperatures hot enough to melt lead. This makes Venus the hottest planet in our solar system, even hotter than Mercury. But it's not just the heat, it's the weight of the air itself. The atmospheric pressure is 90 times greater than Earth's. To imagine that, think about diving 900 meters under the ocean. That's the kind of crushing force pressing down on the Venusian surface at all times. Maya, from a chemical perspective, this is even more intense. The clouds aren't made of water vapor. They are corrosive sulfuric acid. They create a permanent, thick orange haze that traps heat and blocks any view of the sun or stars from the ground. Nova, notice the temperature relationship expressed here. This extreme thermal state is the result of a runaway greenhouse effect. The atmosphere is so thick with CO2 that solar energy enters but can never escape, a process we will dive deeper into in the next segment. It serves as a powerful, albeit terrifying, comparison to Earth's own climate system. Building on what we just covered regarding Venus as Earth's evil twin, let's examine the specific mechanism that makes it so hostile: the runaway greenhouse effect. It's a perfect, albeit extreme, example of atmospheric physics in action. The driver of this heat is the atmospheric composition. While Earth has trace amounts of carbon dioxide, Venus's atmosphere is 96% CO2. This creates an incredibly dense, heavy blanket around the planet. As shown in the flowchart, shortwave solar radiation penetrates the clouds and reaches the surface, where it is absorbed and converted into heat. Under normal conditions, a planet radiates this thermal energy back into space. However, on Venus, the dense CO2 is opaque to infrared radiation. The heat becomes trapped, bouncing back toward the surface and raising the temperature further in a vicious feedback loop. This leads to our critical point: a surface temperature that reaches 462 degrees Celsius. To put that in perspective, that is hot enough to melt lead and far hotter than a kitchen oven on its highest setting. Maya, looking at this data, what does this tell us about the importance of atmospheric balance back home on Earth? Welcome! Today we're exploring how atmospheric conditions determine a planet's temperature. Let's see how CO2 pressure and sunlight interact. This slider adjusts the CO2 concentration. Carbon dioxide is a potent greenhouse gas that traps heat within the atmosphere. Look at Venus. With extreme CO2 levels and crushing atmospheric pressure, the greenhouse effect goes into overdrive, creating a scorching runaway heating scenario. Now consider Mars. Its thin atmosphere and low CO2 levels mean it cannot effectively retain heat, leading to plummeting temperatures and a frozen landscape. Earth sits in a Goldilocks zone. Our balanced atmosphere and distance from the sun keep temperatures stable enough to support liquid water and life. Note how pressure acts as a multiplier. Higher pressure increases the density of gas molecules, making the greenhouse effect even more efficient. Having just explored the extremes of the greenhouse effect in our simulator, let's step back and look at the big picture. Why did these three neighbors, born from the same solar nebula, end up with such wildly different fates? Look at this data comparison. While Earth sits in that comfortable middle ground, Venus is a high-pressure furnace and Mars is a low-pressure freezer. Interestingly, both our neighbors have atmospheres dominated by CO2, yet it is Earth's unique composition that allows for life as we know it. The reason Earth stayed just right isn't just about distance from the sun, it's about active maintenance. Our planet has internal engines that the others lack or lost long ago. First, we have plate tectonics. As we discussed earlier regarding carbon cycles, Earth actually recycles greenhouse gases back into its crust. Without this planetary thermostat, our CO2 levels could have spiraled out of control, mirroring the Venusian nightmare. Second, our global magnetic field serves as a vital shield. It deflects the solar wind that would otherwise strip our atmosphere away. Mars lost its magnetic protection billions of years ago, which is why its atmosphere is now a mere fraction of Earth's. It's a sobering reminder of how lucky we are. Maya, considering your interest in environmental chemistry, how do these planetary comparisons change your view on the stability of Earth's current atmosphere? As we bring our journey to a close, let's reflect on the profound lessons of atmospheric evolution and what they reveal about Earth's future. We've seen that the history of a planet is written in its air. When we look at these planetary comparisons, the most striking realization is that atmospheres are incredibly fragile life support systems. As we discussed earlier, when looking at the Martian thinness, even a small shift in gravity or magnetic protection can lead to a world becoming a desert. These key scientific markers, the red rust of Mars signaling oxidative loss and the extreme heat of Venus, are not just alien curiosities. They are the physical evidence of how chemical cycles like the CO2 cycle can run out of control if the planetary balance is tipped. Ultimately, atmospheric dynamics determine the boundaries of life. By studying our neighbors, we better understand the stewardship required for our own home. Earth sits in a Goldilocks zone, but as we've learned from Venus, that position is maintained by the delicate chemistry of our atmosphere. Before we wrap up our session, I want us to think about how this planetary perspective changes our view of climate change here on Earth. Maya, I know you've been analyzing the chemical parallels between Venus and our own industrial emissions.